All right, if you're an architect studying for your exams, you know that electrical systems can feel like a total black box. But here's the thing, understanding how a building gets its juice is absolutely fundamental to good design. So in this explainer, we're going to demystify all those voltages and configurations that power everything from a single-family home to a skyscraper, giving you the essential knowledge you need to ace those exams.
So let's start with a basic question. Why can't you just plug a massive commercial pizza oven into a regular wall outlet? Well, it all comes down to a really simple truth. Different buildings have fundamentally different power needs. The demands of a house are just worlds apart from a high-rise office tower. And understanding that difference, well, that's exactly what we're breaking down today.
To get why, we've got to start with the two basic flavors of power that a utility company can deliver to your building. This is the first and honestly the most important distinction you need to grasp: single-phase versus three-phase power.
Let's break this down with a quick analogy. Think of single-phase power as just one person pushing a kid on a swing. You get a good push, right? But there's that tiny pause at the top of the arc. It works just fine for smaller tasks. Now, three-phase power, that's like having three friends pushing that same swing perfectly in sync. The power delivery is constant, it's smooth, and it's way stronger. And that is absolutely critical for big motors and things like HVAC systems or elevators. It keeps them running efficiently without a lot of vibration.
Okay, so let's start with the system we all know best, residential power. Once you really get how our own homes are wired, it's the perfect stepping stone to understanding the more complex systems we're going to see later.
The standard for pretty much every house and apartment in the US and Canada is called 120/240 volt split phase. And it is a really clever and versatile system. It takes that single phase of power from the utility and using a special kind of transformer, it splits it. This gives us two different voltages from just three little wires.
So here's how that little bit of magic works. You get two hot lines and one neutral wire coming into your house. If you connect either one of those hot lines to the neutral, boom, you get 120 volts. That's perfect for your laptop charger, your lamps, your TV, all the standard stuff. But if you connect the two hot lines directly to each other, you get the full 240 volts. And this is what powers your heavy hitters, your big electric dryer, your oven, or your central AC unit. It's a super efficient way to handle all of a home's different needs with just one simple service.
Okay, let's scale up. We're moving from a house to your typical Main Street business, like a restaurant, a little retail shop, or a small office. Their power needs are a lot more demanding, and that calls for a totally different system. For these kinds of buildings, the go-to system is 120/208 volt three-phase. This is the absolute workhorse of small commercial architecture. Now notice two things right away. We've officially moved to three-phase power, and we have a new voltage in the mix, 208 volts. This system is so common because it gives you the best of both worlds. You still get that 120 volts you need for all the standard outlets and lights, and you get a more powerful three-phase supply for commercial kitchen equipment, small motors, and rooftop HVAC units.
So where in the world does this weird 208 volt number come from? This is a key piece of information, especially for your exams, so listen up. In this type of three-phase system, the voltage between any two of the hot lines isn't just 120 plus 120. Because those three waves of power are out of sync with each other, the math is actually 120 volts times the square root of 3, which gives you about 208. That's the voltage that powers all that crucial commercial equipment. And this is what it looks like in the real world. This panel board is the physical heart of the system. It's the distribution hub. Now, as an architect, you're not going to be designing the circuits inside it, but, and this is super important, you absolutely have to design the space for it. We'll come back to that in a bit. But this is where all that power gets divided up and sent out to the lights, the plugs, and all the equipment.
All right, time for the big leagues. Let's talk about high-rises, huge institutional buildings like hospitals and factories. In these places, the power demand is just massive, and efficiency is everything.
In these larger buildings, the standard gets a major upgrade to 277/480 volt three-phase. Think of higher voltage like having higher water pressure. It lets you do a lot more work with less energy lost over long distances. That powerful 480 volt three-phase supply is perfect for gigantic HVAC motors, elevators, and big pumps. And the 277 volts? Well, that's just 480 divided by the square root of 3. And it's extremely common for running long rows of high-efficiency fluorescent and LED lighting in big commercial spaces.
But wait a minute. What about plugging in a computer or a desk lamp? You can't just plug that into a 480 volt circuit. That's where this piece of equipment comes in. Large buildings use these transformers to step down the high voltage power right where it's needed.
It takes that super efficient 480-volt supply and safely converts it down to the familiar 120/208 volts for your everyday wall outlets and standard office equipment. So you really get the best of both worlds: high voltage efficiency for all the big stuff and low voltage convenience for all the small stuff.
Okay, so let's put this all together on one screen. This right here, this is your cheat sheet for the ARE. Residential, 120/240V, single phase, small commercial, 120/208V, three phase, and large commercial, 277/480V, three phase. If you can memorize these pairings and what they're generally used for, you are way ahead of the game.
So, why does an architect need to know all this technical jargon? Because this theory directly, and I mean directly, impacts your floor plans and your building safety. The National Electrical Code, or NEC, has very specific rules about the physical space around electrical equipment, and you, the architect, are responsible for providing it.
The first big rule is that equipment has to be readily accessible. The code is very clear. That means someone can get to it without having to climb over or move a bunch of stuff. The picture on the left, that's a total code violation and, frankly, a safety nightmare. The one on the right shows a properly designed space. Your job is to design that clean, accessible space from day one.
And that brings us to a critical term you have to know: working space. This isn't a suggestion, it's a legally required three-dimensional zone that you have to show on your drawings. The width is at least 30 inches, the height is 78 inches, and the depth, now this is key, it's 36 inches for a 120/208 volt system, but it increases to 48 inches, a full 4 feet for a 277/480 volt system. As the architect, you have to carve out this clear volume in your plans from the very beginning.
And there's one more zone to protect: the dedicated equipment space. This is a zone that's the same width and depth as the panel, and it extends from the floor all the way up to 6 feet above the equipment or to the ceiling. This space has to be completely free of anything that isn't electrical. No water pipes, no drain lines, no ductwork. And the reason's pretty obvious, right? You do not want a leaky pipe to drip water all over a live electrical panel. This is a huge coordination item for you and your MEP engineers.
Okay, we have covered a ton of ground. Let's wrap this all up with a final review of the absolute must-know info for your PPD and PDD exams.
All right, here it is one last time. Let's burn this into our brains. Residential is 120/240 single phase. Small commercial is 120/208 three phase. And large commercial is 277/480 three phase, which almost always uses those step-down transformers to give you 120/208 for general use. If you remember nothing else from this, remember this slide.
And that really covers the fundamentals of powering buildings. But as sustainability keeps pushing us toward all-electric designs for heating, cooking, you name it, the demands on these systems are just going to get bigger and bigger. So the real question for the future is, how will these core electrical systems need to adapt and evolve? And that's a challenge for the next generation of architects, your generation, to help solve.